For Unit 3, Lesson 3, the set section, I might break this into two videos. Let's just start with questions 5 through 10. In 5 through 10, we are asked to determine if the statement is true or false, and if it's false, explain why. So statement 1, all linear functions are increasing. Well, this statement is false, and let me just show you two counterexamples. If this is my y and my x-axis, I could draw a linear function that is neither increasing nor decreasing. It is constant. Or I could draw a linear function that is decreasing. So this statement is false, and it is because linear functions, I'm having some issues with my computer. I'm sorry if it's cutting out a little bit. Linear functions can be constant, meaning that they're neither increasing or decreasing, so our slope is 0 when that happens, or decreasing. Okay, that one's not too bad. Question 6, or statement 6. Arithmetic sequences are an example of linear functions. This is true. In Unit 2, we talk about how arithmetic sequences, I'm going to just abbreviate ASEQ for arithmetic sequence. We talk about how arithmetic sequences are discrete linear functions. So they are a type of a linear function. I'm just abbreviating for time here in the video, and they're discrete. So that's a true statement. Statement 7, exponential functions have a domain that includes all real numbers. So remember, domain is all of the x values of a function where it exists. And so far, we've only looked at exponential functions that are positive, meaning that their y values are positive, so they're above the x-axis. I'm just going to draw an increasing one. We could have a decreasing exponential function. Like if our growth factor is a fraction, like 1/2, it would decrease. This function's increasing, so its growth factor is a number greater than 1. So if I consider my x values, when I draw this, the arrows at the end, this arrow to the left implies that this function continues forever to the left, and we have what we call a horizontal asymptote here that the function doesn't cross. And to the right, this arrow tells us the function pattern continues, that we are both going up but also to the right forever. So that means that I could draw this function using every single value on my x-axis. So I could define that as having a domain that includes all real numbers. So this statement is true. In statement 8, geometric sequences, so not all exponential functions, but a geometric sequence, has a domain that includes all integers. This is a tough one. I'm going to say that I think typically we would define a sequence as having a domain of natural or counting numbers. So I'm going to say natural. We said sometimes we call natural numbers counting numbers. So think about numbers you count with, 1, 2, 3, or whole numbers. So the set of whole numbers, remember, is all of our natural numbers, but it also includes the number 0. So in Unit 1, sometimes we worked with geometric sequences, and we had this phrase like at the beginning that kind of implied that our input was 0. So, this question's actually a little iffy for me. I'm going to go with false though, because typically our domain would be natural or whole numbers. All right, question 9. The range for an exponential function includes all real numbers. So this statement is also false. And I want to just note that you will learn later on about functions that are negative. But up until now, all of the exponential functions we've looked at, I'll draw a decreasing one. They've all oops, that's not very good. They have all been functions that have only positive outputs. Now, not all exponential functions are like that, but the one I just drew is. So the range for an exponential function is not going to be all real numbers, because remember, the range is all of our y values or outputs, and the function that I just drew has a horizontal asymptote where y equals 0, and that function is never going to cross that line to the right. It's going to get close to 0. So maybe this function is like y equals 1/2 to the power of x. Well, if I keep putting in greater x values, my y values just become half of what they were before. But if you keep cutting something in half, it technically never becomes 0. It just gets smaller. So that's why this statement is false. All right, lastly, number 10, all linear relationships are functions with a domain and range containing all real numbers. I think often the linear relationships we'll work with have a domain and range containing all real numbers, but I could think of two counterexamples. We could first of all, so this is just my x and my y axis here, we could have a linear relationship that's constant. So a linear function that's constant. The domain for that function would be all real numbers, but the range for that function would just be whatever value that function goes through. Let's say that this goes through the y-axis at where y is 5. The range would only be the number 5. That would be the only output. Another way we could prove this statement is false is, let's imagine a discrete relationship. Maybe we have an arithmetic sequence. That's a type of linear relationship. Well, now my discrete function does not have a domain of all real numbers, nor does it have a range of all real numbers. So we're going to say this statement is false. We could think of a discrete function. So discrete functions do not have a domain or a range of all reals. So I'm going to say all real numbers. I'm going to use that symbol that kind of looks like an R that's double outlined. All right, I know there's a few more questions. They might take a little bit longer to talk about, so I'm just going to make that in a second video.